All right, so on to our learning unit on lipids. And just to highlight, when we talk about lipids, generally that's just referring to any sort of substance that's hydrophobic or nonpolar. And so lots of things are going to fall into this category. And so this is the fourth of the macromolecules that we're learning about. We already learned about nucleic acids. And again, just doing a little review here, nucleic acids are built from nucleotides that are hooked or linked together by a phosphodiester bond. Then we learned about amino acids, which are hooked together by an amide or a peptide bond to make proteins. We just finished our learning unit on carbohydrates, and that takes monosaccharides, simple sugars, hooks them together by a glycosidic bond to make our polymers. And so those are three very traditional polymeric materials, and they're also very water soluble. So this fourth sort of one is in a little bit of a class of its own, not only because it's not very water soluble, so we're going to have to focus on transport issues, okay? But secondly, it doesn't really polymerize the way we think about our other monomers that form polymers. We are going to talk about a linkage though, but it's not going to be a linkage that generates polymers. And that's going to tie us into sort of this first sort of structural piece that we're going to learn about. We don't have monomers like we have nucleotides or amino acids or monosaccharides, but we do have fatty acids. And so when I talk about fatty acids, this is going to be what I'm talking about. One finger represents a single fatty acid. We're going to talk about putting two of these fatty acids together. We're going to hook them onto a 3-carbon, each of my knuckles represents a carbon atom, a 3-carbon backbone that we call glycerol. Okay, that's going to generate phospholipids. And then 3 fingers is going to generate triglycerides. So that's sort of what we're building up here. And the linkage that we have, how we link my fingers to my knuckles, that linkage is going to be an ester linkage. And we're going to see the chemistry that happens here in a little bit with that. So let's talk a little bit about the building blocks that we have for these phospholipids or triglycerides. And the building blocks are fatty acids. Okay, so sort of highlighting the pieces that we have here, we've got a very hydrophobic tail here. Okay, so this is our hydrophobic tail. And to sort of map it onto the anatomy of my hand here, that's the bulk of my finger here. And then we also have a hydrophilic head group. Okay, so we've got a hydrophilic head group. So hydrophilic head. Okay, and that again is because we've got a carboxylic acid group. They show it there as a protonated carboxylic acid, physiological pH that's likely to be deprotonated, so it will be negatively charged. Mapping on what we see anatomically with my hand, that's my knuckle. Okay, so what we have again, and I should say that my knuckles, I sort of said represented my glycerol backbone. Glycerol is a polyalcohol, 3 carbons, each with an OH group. Remember, when we have a carboxylic acid that we hook with an alcohol, that generates an ester linkage. So carboxylic acids here on my fatty acids, when I hook that to the glycerol backbone's alcohol group, I generate an ester linkage, and that's how I hook my fingers to my knuckles here to generate either a phospholipid or a triglyceride. All right, on this slide here, I have 3 different fatty acids. Okay, they fall into 2 categories. The one on the left here is a saturated fatty acid. The ones that we have over here, and we'll get to those in a minute, are all unsaturated. Okay, so we'll talk about what that means here. When we talk about a saturated fatty acid, okay, there are no double bonds. And this creates a molecule that's very stable. Right, so a lot of times we're going to reflect back to things that we learned in general chemistry or in an organic chemistry class. When you learn things in organic chemistry, you tend to learn things by functional groups. And so when you talked about alkanes as maybe a single learning unit in organic chemistry, there probably wasn't a lot of chemistry that you learned about because alkanes, by and large, are fairly unreactive. You may have learned about some radical chemistry, but they're fairly unreactive. And that's going to be an important piece that we think about because when we have saturated fatty acids, when we have dietary fats that are made up of saturated fats, they tend to be very stable. They're very shelf stable. That's going to play into some pieces that we'll talk about when we think about what is done to food products to make them be more shelf stable. So saturated fatty acids here, no double bonds in that hydrocarbon tail, that very hydrophobic tail. And so we have a very stable sort of piece here. Another sort of big picture step back to think about thing here. When we talk about things that are made in your body is not going to make things that are bad for you. Okay, 2 things that we'll talk about in this learning unit that your body makes. Your body makes a heck of a lot of saturated fat, and it makes cholesterol. 2 things that in today's sort of dietary space get a really bad rap. Saturated fats are not bad for you. Cholesterol is not bad for you, okay? What happens is sometimes the space that they live in can make them have unintended consequences. And we'll get to those details as we sort of talk about all of those pieces a little bit later on. All right, so those are saturated fats, okay? Let's talk about unsaturated fatty acids. And we essentially have 2 flavors that we have here in terms of unsaturated, okay? We're going to have what we call mono unsaturated, and then these guys are poly unsaturated. So just to remind ourselves what it means to be unsaturated. So unsaturated means we're going to have 1 or more double bond. And we're going to talk about in a couple minutes like some of the details that we have for those double bonds, okay? But when we look at where those double bonds are, mono unsaturated fatty acids only have 1 double bond. Polyunsaturated are going to have more than 1. Here we can see 2 and then 3 double bonds that we have there. So 3 things that I want you to remember about these fatty acids that sort of make them be sort of what we see in a natural situation is the configuration that we see is the first part. So we always see these in naturally occurring fatty acids being the cis configuration. Okay, we look at what we have here. Remember, double bond configuration or geometries can come in cis or trans. If I look at the position of the 2 smallest substituents on a double bond, the hydrogen atoms, they're on the same side. So again, all of these double bonds are cis, and we can see those sort of by the geometry that we have about that double bond looking at those hydrogen atoms. From a structure function standpoint, we're going to map this on in another video coming up here with why that's important. When I show my finger like this, nice and straight, that's what we have when we have all sp3 hybridized carbon atoms. They're going to give as much room as possible, and so we're going to see a nice linear molecule here. When I have a cis double bond, that introduces a kink. Okay, so this adds a kink in that's going to have a lot of implications in terms of the physical properties that we see. So this is going to add in a kink or a bend, okay? So the first thing I want you to remember about naturally occurring unsaturated fatty acids is the double bond geometry is always cis. Trans, we're going to talk about trans fats a little bit later, but again, that is a different geometry and that is not in general naturally occurring. A couple of other pieces to add in. These double bonds, when we have polyunsaturated fatty acids, those double bonds are never in conjugation. So never in conjugation. So remembering what it means to have double bonds be conjugated, that means we essentially, every single carbon atom in a row is part of a double bond. You said another way, you have sp2 hybridized carbon atoms that are all in a row. So when we see sp3 hybridized carbon atoms that sort of break up that repeating sort of double bond structure, that alternating double bond structure, that disrupts that conjugation. These double bonds are not in conjugation. We don't see that with fatty acids. There's lots of biological molecules that have conjugated double bonds. We talked about that, for example, with something like beta carotene. When you have a lot of those double bonds in conjugation, that increases sort of the ability to sort of have resonance. And what we see with those extended conjugated systems is we move absorbance values, absorbance max, lambda max values into the visible spectrum, right? Beta carotene's orange in color. That's why. So the last piece that I want you to know about the double bonds that we see in naturally occurring unsaturated fatty acids is that we never see them before carbon 9. So if we look at where the 9th carbon is here, okay, there's the 9th carbon. We never see any units of unsaturation before carbon 9. And that's just how naturally occurring fatty acids are built. One other thing to sort of highlight here is when we're talking about what we see, and I'll refer to these as our fatty acids, right? What we see in our bodies is we tend to see ones that are even chain. They are going to have an even number of carbon atoms. It's not to say that there's not odd chain fatty acids, but in terms of what we tend to see in our dietary foods and what we make and use ourselves in our body, they are going to be even chain fatty acids. Okay, we can see here with all of these that we have in our examples here, they're all C18 fatty acids, 18 carbon atoms. Okay. I want to talk a little bit about the last two that we have here. We've got linoleic acid and linolenic acid. These are two really important fatty acids, and that's because one of them is omega-6 and another one is omega-3. You've probably heard of omega fats. Omega fats are really important to a healthy diet, okay? Highlighting why these are called omega fats. Omega is the last letter in the Greek alphabet. So when we talk about omega-3 fatty acids, 3 carbons up from the end is where we have our double bond, the last carbon that's participating in a double bond. 1, 2, 3, 4, 5, 6. This is an omega-6 fatty acid. Okay, so we've got, again, omega-3 fatty acids. Those omega-3 fatty acids have the double bond. Last part of a double bond, the last sp2 hybridized carbon is 3 carbons in from the end. And then we have omega-6 fatty acids, where we're going to have that last sp2 carbon is going to be 6 in from the end. Okay, some important things that I want to highlight, review with you about omega fats. We're going to get into a deeper dive in another video here. These are essential parts of your diet. Now, this is really important when we use the word essential. Essential doesn't mean necessary. There's lots of things in your body that are necessary. Glucose is necessary in your body, but glucose is not essential. And even though those words might be sort of synonyms in terms of our English language, they have very different meanings when we talk about them biochemically. So when we have something that's necessary, when we have something that is necessary, your body needs it. You need glucose, but you can make glucose yourself. Okay, something that is essential means you cannot produce it and you must consume it in your diet. So cannot produce and must consume in your diet. So that is the definition of something that is essential from a dietary standpoint, okay? Last piece to highlight here is why we need these omega-3 and omega-6 fatty acids. Again, they're necessary, but also essential. So why are they necessary? Well, omega-3 fatty acids are anti-inflammatory. Okay. Omega-6 are pro-inflammatory. And you might ask the question, well, why do we need both of these? It seems like it's, sort of a yin and a yang, if you will. And that is true. And you might say, well, Dr. Perenni, you have told me so many times that inflammation is bad. Inflammation is not bad in an acute sense, right? Inflammation is really good, for example, if you've got a cut and it needs to heal, right? Or if it got infected, right? It's going to become inflamed, and that's because your body recruits all sorts of necessary components to create that inflammation and help rid your body of whatever infectious agent is causing that infection, right? You have a sports injury, right? You have inflammation at the site of that injury, and that brings increased blood supply, all kinds of important nutrients that are going to facilitate the healing. So inflammation is not problematic in an acute sense. The problem with inflammation is if it's chronic. Chronic inflammation is going to be problematic. And we'll kind of have that thread that we'll bring up throughout the course here. So inflammation is good, okay? And so that's why molecules like omega-6 are necessary, because they facilitate that inflammatory cascade. They're part of that inflammation process. But just like you need to sometimes quell that inflammation, omega-3s are important for that. So here's where this becomes problematic with what we call the SAD, the SAD, the Standard American Diet, the SAD diet, okay? We are very heavy in our omega-6s that are in our diet. The fats and the oils that we consume in a lot of our processed food products are very rich in omega-6. So we have a very uneven balance of omega-6s to omega-3s that we consume. And when we have that extra video here that we'll have specifically talking about omega fats, we'll sort of talk about where we get these from dietary sources and how we can try to have a more healthy balance between our omega-6s and our omega-3s. All right, so introductory video here talking about structure of fatty acids.